In our group, we're motivated by the fact that the exploration of underwater environments could yield advances in things like species discovery, or even more so, we could yield advances in the development of climate prediction models, which could better help us identify natural disasters a lot earlier. So we ask ourselves, how do we achieve these advances? Well, we must reliably explore the ocean. And as of today, a shocking 95% of the world's oceans remain unobserved. So how exactly do we communicate in these underwater environments to explore this remaining 95%? One approach is the use of acoustic modems. However, these consume power in the watts range, which implies shorter deployment times. On the other hand, our group, Signal Kinetics, has developed a new method for communicating in underwater environments, known as underwater backscatter. This consumes power in the nanowatts range, and it's able to do this by either absorbing or reflecting existing acoustic signals by turning a switch on or off. Now, given that we have this reliable method for communicating in underwater environments, we recognize that little work has been done on building a sensing platform on top of underwater backscatter. This is exactly where my project comes in. This summer, I investigated the development of a low power, high accuracy, and high resolution sensing system for underwater environments built on top of underwater backscatter. Now, the reason this is challenging is because with the benefits of increased accuracy and increased resolution, we also recognize that it comes at the cost of increased power consumption. So I'll be exploring the trade-offs and trying to balance these. We start off with two measurements that we'd like to take in underwater environments, one being depth and the other being temperature. And here I'm showing you our circuitry. I note that for our depth sensor, we had to mechanically package the device so that it be fit to withstand underwater environments. For our preliminary analysis, I'm showing you here graphs of error and resolution across temperature. So just taking our temperature circuit as an example, I'd like to show our maximum error and minimum resolution. Looking at the graph for error, we know that within our temperature range of 10 degrees Celsius to 30 degrees Celsius, which by the way, is the historic temperature ranges of the Charles River in Cambridge, Massachusetts over the past 5 years, we note that the maximum error of our setup comes to about 0.0019 degrees Celsius. In addition, our resolution comes to about 0.005 degrees Celsius, and we define resolution as the minimum change in temperature that can be recorded. In addition, we recognize that the maximum power consumed for our device is around 4,000 microwatts, when our target is only 360 microwatts. This proves to be challenging. But one way we can overcome this is by duty cycling our microcontroller, where we turn it off and we turn it on to log data and consume the 4,000 microwatts, so that its average power consumed comes down to our target of 360 microwatts. And as an example, we could turn our microcontroller on for approximately 5 seconds every 60 seconds and have the average power consumed come down to 360 microwatts. In the future, we hope to repeat this analytical analysis for our depth sensor and move on to testing in the Charles River. Thank you.